Greetings, I am SM Mahfouz. I will be presenting on TTL NAND gate. In this presentation, I will briefly cover transistor-transistor logic, basic structure of TTL NAND gate, working principle of different input conditions, and noise margin of TTL. TTL stands for transistor-transistor logic. It's a logic family that uses bipolar transistors or BJT to perform both logic operations and signal amplification. After introduction in early 1960, it quickly became one of the most popular logic family because of its high switching speed, reliability, and ease of implementation. Standard TTL circuits operate from single 5-volt power supply. They also provide good noise immunity and moderate fan out, allowing one output to drive multiple TTL inputs. One of the most popular TTL series is the 7400, 7402, 7404, and etc. We can see a couple of those ICs here in the figure. Let's start with the basic structure of TTL NAND gate. Here we can see a double emitter BJT at Q1, which can be realized as this figure. Here we can see this double emitter BJT can be constructed from single emitter BJTs. Like if we connect the base and the collector nodes together, then it can work as a double emitter BJT. And here, this part of the circuit is known as the phase splitter. If we focus on the phase splitter transistor Q2, when the voltage level at the collector node of Q2 is decreases, the voltage level on the emitter node of the Q2 increases. This creates two opposite voltage level that controls the output transistor Q4 and Q3. Let's say we have two inputs at low logic conditions. If we give A and B equal to 0.2 volt at the input side of the emitter of Q1, in order to have a forward um, bias at the base emitter junction, we need at least 0.9 volt at the base node, and that would give us 0.3 volt at the collector node if we assume there is a 6.6 voltage drop at the base collector region. If we assume it's in the forward bias, then this 0.3 volt at the base of Q2 isn't sufficient enough to drive Q2 and Q3. Because of that, the Q2 and Q3 will remain off in this situation. As Q2 is remained off and VCC, if we approximate as 5 volt, there is no current flow through the Q2. So all the current will flow through R2 and Q4 transistor. And as there is no current flow through the Q2, the collector node of the Q2 will remain at high voltage level. If we assume it's nearly at 5 volt, then from here we can calculate the output voltage. As the current flows through the Q4 and D1, there will be 0.7 volt drop at the base emitter junction and the D1 diode. And from there, if we calculate the output voltage, it would be 3.6 volt. As we calculated from the base of the Q4 transistor. So this 3.6 volt can be registered as a output high signal, and this situation, if we in this situation, if we compare it to the NAND gate truth table, it satisfies the condition. Let's say we have a high voltage at input and a low voltage at the input. Then, in this condition, if we consider 0.2 volt to the A node and 5 volt at the B node, then in this case, if we want to operate the Q1 transistor um, at the base emitter junction at forward bias situation, then we need at least 0.9 volt at the base, as there would be 0.7 volt drop at the base emitter junction. And as we saw previously, if this base is at 0.9 volt, then at least there would be a 0.6 volt drop at the base collector junction, and that would give us 0.3 volt at the base of the Q2. Now, this 0.3 volt is a very low voltage, and it is not sufficient to turn on the Q2 and Q3 transistor, so they will remain off in this case. And as I saw in the previous case, if these two transistors are remained off, then all the current flows through the Q4 transistor, and there will be 0.7 plus 0.7, 1.4 volt drop, and we can calculate the output voltage from the base of the Q4 node, and from there we can calculate it 5 minus 1.4 volt is equal to 3.5 volt, 3.6 volt at the output node, and this can be registered as a high signal at the output, and this satisfies the condition of the NAND gate for any of the input is at high voltage and the other is at low voltage. So let's say we have both input as a high in this situation. So we can give A equal to 5 volt and B equal to 5 volt. Here, if we want the base emitter junction working as forward bias, then at least we need 5.7 volt at the base of Q1. But as we can see, the VCC is at only 5 volt. It cannot generate 5.7 volt. So let's assume we have the most voltage, which is 5 volt at the base of Q1. So if we have 5 volt at the base, then the collector would be 4.4 volt. If we assume its base to collector junction is at forward bias mode, and there would be 0.6 volt drop at the base collector junction. Now, in this case, as the base of Q2 is 4.4 volt, it would be sufficient enough to drive this Q2 and Q3. And in this case, there will be current flow through the Q2 and Q3 as they are remained on in this condition. Uh, Now, as you can see, there would be 0.7 volt drop at the base emitter junction of Q3. So, if we accumulate this voltage 0.7 volt at Q3 and 0.7 volt at Q2, then we can see that the base of the Q2 will have 1.4 to 1.5 volt potential instead of 4.4, because there is only 1.4 volt drop across this Q2 and Q3. So there would be 0.6 volt drop across the Q1 collector base collector junction. So the base cannot be higher than 2.1 volt in this case. So in this case, we can see the emitter has higher voltage than the base. So the base emitter junction is in reverse bias mode, and the base collector junction is at in forward bias mode. This satisfies the condition for reverse active mode for Q1. So it will be operating in a reverse active mode condition. Now, if we focus on the Q2, as the transistor remains on, there will be current flow through this transistor. This current flow will drastically reduce the voltage of the collector node of Q2. This low voltage cannot drive Q4 and D1, so that there will the Q4 transistor would remain off, so there would be no current flow through this Q4, and from that we can assume the output voltage is very low. Now, from the perspective of the base of Q3, we can see it has 0.7 volt of potential, which is high enough to make the base to emitter junction for forward bias, and base to collector region is also in forward bias because, as we said before, the collector has a very low voltage as there is no current flow through the Q4. So the base emitter and the base collector junction both are in forward bias mode, which satisfies the condition for saturation mode operation for Q3. And as we know, when a BJT works at saturation mode, there is only 0.2 volt drop across the collector and the emitter. So the output will have a zero point 0.2 volt of potential, which can be registered as a low output signal, and that satisfies the condition for NAND gate when the both inputs are high. Let's briefly talk about the noise margin. The noise margin is the maximum unwanted voltage that can be added to a logic signal without causing an incorrect logic. From this figure, we can see the input and the output range for a TTL device. From the figure, if we calculate the high noise margin, then we can see the high noise margin is around 0.7 volt, and low noise margin we can get 0.3 volt. This means if the electrical noise is introduced during the signal transmission, the receiving TTL gate will still correctly recognize the logic level as long as the noise remains within these margins. That concludes my presentation. Thank you very much for your time and attention.